We're taking a look at our homework on page 259 from last night. Specifically, question number 2 here on page 259. It says, automotive manufacturers test the handling ability of new car design by driving a prototype on a test track in a large circle, a radius 100 meters in this case, at ever-increasing speeds until the car begins to skid. A prototype car of mass 1,200 kilograms is tested and found to skid at a speed of 95 kilometers per hour, which, remember, we want to convert that to meters per second. What is the coefficient of static friction between the car tires and the road? This is, although it's not particularly important in this question, we talked about this a little bit yesterday, right? It is static friction here that we're dealing with because the car isn't sliding, the car isn't skidding. Now, if it goes above 95 kilometers per hour, then it skids. Then we're dealing with kinetic friction, right? Well, that's why a car becomes a lot more difficult to handle when it's skidding, is because we've got kinetic friction, and kinetic friction isn't as big as the maximum force of static friction. So it is static friction here, although in the end for this question, it's not really a major factor in how we're going to tackle this question. What do you want to do? What do you want to do for this? Everybody in this room should have something for this. Everybody in this room should have something written down. There's nobody that should look at this and say, I have no idea what to do. If you say to yourself, I have no idea what to do, you're not giving yourself enough credit, because everybody has some idea. Now, you might not be able to solve the question, but everybody has some idea. What is applicable here? What is valid here? What's going on in this question? Brogan? Okay, we could solve for friction, right? Or at least we could write down the friction equation. We're looking for the coefficient, so I'm not sure that we're actually going to be able to solve for the value of the force of friction. Oh, okay. So, let's do one thing at a time. But Brogan recognizes that there is a force of friction here, and we want to find a coefficient. And the only way to find a coefficient of friction is to use the equation F is equal to mu times Fn. We're going to rearrange this. We're going to say mu is equal to the force of friction over, we're going to say it's m times g. On a flat horizontal surface, that normal force is usually going to be m times g, right? Unless there's some other force pulling up on it as well, like the wagon problems. But I don't know what force of friction is, so some of you at this point might be at a little bit of a loss. Okay? Some of you might not. In the end, Brogan told me just a second ago that if we don't have that force of friction, basically she said, find it. Find it some other way. Well, what else applies here besides friction? Yeah, absolutely, absolutely. This is going in a circle. Every time something goes in a circle, we know it experiences a centripetal force. So if we find the centripetal force, oh wait, centripetal force, remember this? We said centripetal force is never fundamental. It's always caused by something. When I swung the keys around my hand, the centripetal force was caused by my hand. So Fc would have been equal to F hand, whatever that is. In the case of the Earth going around the sun, the centripetal force was caused by gravity. It's always caused by something. Now, we don't always need to use that to solve a problem. Sometimes it's good enough just to say mv squared over r and we're done. But if we're not getting an answer just using mv squared over r, well then try setting it equal to something. The centripetal force here is, let's say, 1,200 kilograms times v, which is 95 kilometers per hour was what in meters per second? 95 times 1,000 divided by 3,600, what was it, Janae? 26.38 meters per second. Square that, divide it by r. R is 100 meters. Let's say 1,200 times 26.38 squared divided by 100. 8,350.85. Okay, so there's my force, my centripetal force, but the centripetal force is caused by friction, so they're going to be equal to each other. So let's just do this then. Let's say 8350.85 divided by the mass of 1,200 kilograms times 9.81. I see some brackets on the bottom, 1,200 times 9.81, and we end up getting a coefficient of 0.71, or 0.709, I guess. Does that seem reasonable? Sure it does. You get an answer that's 27, then it's not reasonable, right? But 0.709 seems very reasonable. Now, did anybody, like everybody had to do it more or less like this, but did anybody structure it a little bit different? Yeah? What'd you do? Oh, okay, so you set them equal to each other right off the top. Yeah. You know what, honestly, that's what I would do as well. But I'm glad Brogan said this first, because it makes a good point. Okay? If you notice, if you recognize right away that FC is equal to FF, that's wonderful. But sometimes you won't notice things like that right away, right? Sometimes you're not going to know exactly what you have to do to solve the problem. But there's always something that you know. Hey, Brogan wrote down F is equal to mu times Fn separately from the centripetal force because she knew that applied. And then later on, she knew this applied. And then it kind of went together and ended up working out. Okay? If you know that Fc equals Fn, F right away, great. The one benefit of doing it that way, of doing it your way, setting them equal to each other right off the top, is that the masses cancel, right? So, I mean, if I had a different mass here, 2,800 kilograms, I would have got the same answer because the mass ends up canceling if you set them equal to each other. But I had to use the mass the way that we did it here. Yep.
We do F equals sometimes A and then find acceleration and then do it like that.
Okay, how would you find acceleration there?
I don't know.
Okay. I'll answer your questions in a second. Yeah, go ahead. Yeah. No, absolutely. Okay. Could you use F is equal to M times A? Absolutely. Is there a force here? Is there a force here? Then absolutely you can use F is equal to M times A. Absolutely. But what's A? How'd you find it? What equation? What kind of acceleration is it when it's going around in a circle? Centripetal acceleration, right? So if we replace A with V squared over R, then what do we end up with for this force? M times V squared over R, which is the centripetal force, right? So, like, it's thoughts, right? It's correct, valid thoughts. Try them. And it's just amazing how oftentimes, not always, but oftentimes things just kind of fall into place and you end up getting an answer. Okay? If you sit there and say, I don't know how to do this question, and don't write anything down, then nothing's going to fall into place. If you try stuff, then it's amazing how sometimes, at least, things just come into place when you didn't know what you were doing necessarily completely when you started the question. All right, I'm going to give you one more question just as a little practice. Call it a practice quiz if you want, because we're going to see something like this on a little quiz on Monday. Centripetal acceleration, centripetal force, including the questions that we just did. Give you a couple minutes to work on that, and then we'll take a look at this real quickly as a group when you're finished. So the question says a 1,500 kilogram car goes around this 100-meter radius at the maximum possible speed before it begins to skid. What is that maximum possible speed if the coefficient of friction is 0.75? What kind of friction would it be, by the way? Not that it really matters to this question. It'd be static because you're not sliding, right? You're not skidding or sliding. I'm going to do it Megan's way this time, which is to right away set FC equal to FM. If you don't notice that right away, no, sorry, not FC equals FM. FC equals Physics 30 we just finished. We just finished talking about magnetism. And in a magnetic field, when a charged particle goes in a magnetic field, it ends up following a circular path in that magnetic field. So how do we analyze it? We say FC equals Fm. The centripetal force equals the magnetic force. And I've just done that so many times in the last couple weeks that I kind of just forgot what we were doing there. But it illustrates nicely that, again, that the centripetal force is always caused by something. In that case, when the charged particle is in the magnetic field, it's caused by the magnetic force. In this case, it's caused by the frictional force. So set them equal to each other if you spot that. If you don't, that's okay. Just do something that you know, like FC or like FF, and then hopefully spot the fact that they're equal to each other later on. mv squared over r equals mu times Fn. I was about to write down another equation again, the equation for magnetic force. Almost made the same mistake again. Fn, by the way, is equal to what? Like it's a flat, simple horizontal surface, so Fn is equal to m times g. Nice thing about setting them equal to each other like this is the mass cancels. We've got v squared over r equals mu times g, and we're solving for v here. So it becomes the square root of mu times g times r. Square root of 0.75 times 9.81 times r was 100. I think when we did that, I think it worked out to be 27, wasn't it? 27 meters per second. Okay, how many people got 27 for that? Okay, good. Good. You can see maybe if you were going to become an engineer that designed highways, knowing something about this would be useful, right? You design a highway. Maybe you want to design a highway to hold cars at 100 kilometers per hour. Well, do a calculation like this to see what the radius of the turn needs to be. Or maybe you're limited by geography and you have to have a certain radius and you want to determine what the speed limit should be. If I can be going maximum 27 meters per second before I skid off the road, then I probably want to make the speed limit something less than 27 meters per second, right? Okay, probably a fair bit less than 27 meters per second, but certainly less than 27. Make sense? All right. Now, over the last few days, we've talked about, or the last couple of days, we've talked about centripetal force. Centripetal with a P as being that force that acts toward the center of the circle. We call it sometimes a center-seeking force because it does act toward the center of the circle. Centrifugal force is that force that is center-fleeing. Or in other words, that force that pushes something out from the center toward the outside of the circle. But notice I've got centrifugal in quotation marks. I really should have force in quotation marks as well. Because the centrifugal force, that force that pushes something out from the center of a circle, doesn't really exist. So how do we explain how we get pushed out to the outside of a circle when this force that pushes us out to the outside, that we feel, that we've all experienced, that we've all felt? How do we explain how we've all experienced a force pushing us outward, but it doesn't exist? Well, it's not really a force pushing you out at all. It's really just... Talked about this a little bit the other day, but kind of outside of this context, you might not remember it. It's really just your inertia. You want to go in a straight line. You want to go in a straight line. So let's say you're on that merry-go-round. Here's the merry-go-round. It's going counterclockwise like this. Here's the center of the merry-go-round. And you're at this bar of the merry-go-round right here. There's your position. But you're rotating counterclockwise with the merry-go-round. Here's a spot on the outside of the merry-go-round that's rotating counterclockwise, right? When you look out, you see this red dot. When I was in elementary school, we had a merry-go-round, and there was this one bar that had this like deep scratch in it. And I don't know why, but for whatever reason, nobody ever wanted to be on that bar. Like everybody wanted to be on, there was 4 bars, everybody wanted the other 3 bars. Nobody wanted the bar with the scratch. It wasn't sharp or anything, it didn't hurt anybody, but everybody avoided that bar. Okay? Let's say that this is the scratch on that bar. Okay, this red is the scratch on that bar. I'm on this bar, okay, or I'm holding onto this bar, or I'm beside this bar, and I'm looking out and I see this scratch. Okay, now when I look out a tenth of a second later, where is that scratch? It's right here, right? Where am I? Right here. Agree? Tenth of a second later, where's the scratch? Right here. Where am I? Right here. Tenth of a second later, where's the scratch? Right here. Where am I? Right here. What was the path of this scratch? Circle, right? It was going in a circle. But me, who's not attached to this thing, who got, like, look at it one step at a time here. Right here, I'm closer to the center. And then I'm a little bit further out. And then I'm a little bit further out. And then I'm all the way out. From my perspective, I went straight out. Right? I feel like I went straight out. But which way did I really go? Which way did I really go? In a straight line. It's my inertia. What force pushes me to the outside of the circle? Nothing pushes me to the outside of the circle. That centrifugal force that we call that force that pushes us to the outside is really just you wanting to go by Newton's first law in a straight line. It's really just your inertia. Does that make a little bit of sense? Now, let's say that there was a wall out here. It's not just a merry-go-round with bars. There's actually a wall out here. Now that I'm at the wall, like, now I'm not going anywhere, right? I'm just getting pinned against the wall. But I sure feel like I'm being pushed outwards, right? Okay. So now it's not just appearing to me as if I'm being pushed outward. Now I physically feel like I'm being pushed outward. But just like when you sit in your car at a stoplight and then put your foot on the accelerator, you feel like you're being pushed back against your seat, right? Especially if you accelerate quite quickly. Fly on an airplane, you turn that corner to go onto the runway, and the pilot just gives her, and all of a sudden you're going from 0 to 300 kilometers an hour in just a few seconds. Like, you feel like you're being pushed back against your seat. Are you? No, it's your seat pushing you forward. Whenever there's a force pushing one way, there's a pseudo force or a fake force. It feels like you're being pushed the other way. I'm being pushed inward from the outside, pushed into the center by the centripetal force. What does it feel like to me? I'm being pushed outward. Just like when I accelerate forward in my car, I feel like I'm being pushed back against my seat. So we could say it's really just inertia. Well, sometimes it's inertia and the centripetal force. When I'm moving to the outside like it was in this green line, that's just inertia. But when I actually make it to the outside and I feel like I'm being pinned against that wall, well, then it's my inertia that wants me to continue going in a straight line, but the wall or the centripetal force is keeping me from going in a straight line. It's preventing me from going in a straight line. Does that make sense? Now, we talked a little bit before about the normal force being the apparent weight. Do you remember that? Your normal force is your apparent weight in an elevator question. If I solve for the normal force, I'm solving for how heavy I actually feel. Remember? If you're pinned against one of those amusement park rides that spins around, okay, the force of the wall pushing you in would be your normal force. And that would be how heavy you would feel. So you can imagine if you spun around fast enough, my weight is 700 newtons. My force of gravity is 700 newtons. You can imagine if this ride was spinning around fast enough that the centripetal force was 700 newtons and I closed my eyes, what would happen? I'm spinning around fast enough to make the centripetal force 700 newtons and I close my eyes. What happens? What do I feel? What do I perceive? I don't know which way's down. Think about that. Now I'm being pinned against this wall. Really, it's the wall pushing me in, But it feels like you're being pinned against this wall with 700 newtons. Gravity's pulling down with 700 newtons. How do I know when I have my eyes closed which way's up and which way's sideways? Okay, spin around a little bit faster, and it would actually be easier to walk on the wall than it would be to walk on the ground. Make sense?